Line exams are with your supervising teachers already. I sent them out this morning, uh, early this morning, about 9 o'clock-ish, 10 o'clock-ish, right, just before we started here. So the exams, the final exams are in the hands of your supervisors. So that means during your exam week, they're ready to go, or if you have them scheduled a little bit earlier or whatever, if you do them the day before final exams or whatever, if you have a different exam schedule than what we have in Vanguard, that's fine. The only stipulation is I need them before or on at the latest in the morning, the 29th, because I have to do my report cards by the end of the 29th, which, if I get them on the 29th, I only have 12 physics students, or 13, I think. So it wouldn't take me that long to go through your exams, a couple hours. All right, so, oops, I just had that where I wanted it. So, modern physics part. Okay, we only did 4 days of it. And the main formula that we're going to be looking at using is for nuclear binding energy and nuclear energy of fusion or fission, is this one. And that's basically the only formula. We didn't do anything with Planck's constant or any of that stuff. Sometimes we do, sometimes we don't, but that's mainly university stuff called quantum physics and things like that. And then, of course, the constant of C. Okay, so that's your values for the modern physics part of your exam, right? Now, in terms of the particle masses and the particle weights, I will put them in the question, so you don't have to write them down, what a neutron is, what a proton is, none of that stuff. You don't have to worry about that. Okay, that's all in there. I've also included on the exam on the front page one of these here charts, a periodic table like this, one here, just so that when you're doing nuclear decay, you can count an alpha particle down or a beta particle down and find out where it is. A lot of the nuclear energy stuff happens down here and here. So looking at the bottom of so if you're searching your periodic table, look down there, okay? But the basic formula, this is the only formula really that we're going to use. So in here we have three main types of questions. We have a half-life, we have a nuclear decay or a nuclear fission, and then we have a binding energy. So let's start with the easiest one. Let's do a decay particle, a decay equation. Okay, so I will ask, so you should know what an alpha particle is. So you can put that on your formula sheet. A beta particle. Okay, you can put that on your formula sheet. Of course, the shorthand for each of these looks like that. Okay. Now, do we need the gamma ray? No, because the gamma ray won't be on the exam, so don't worry about that gamma ray one. Okay. So the question, it's going to be 2 marks only. I'm going to ask you to do a decay. So I might have something like this, for example. Write the alpha decay particle equation for, let's use one of the radioactive elements down here. Let's use thorium. Thorium 231. Okay, so step one. First thing we do, we look up thorium on the periodic table. It's element 90. Remember, when you're, this is right, when you're looking at the nuclear particles, uranium's in here and radium's in here. So look at mainly in the 3 bottom rows a lot, okay? A lot of them are there. Some of them aren't. Some are in the, up higher, like potassium and carbon are up way higher. Carbon 14, potassium 19. But we're going to use the heavier elements for these ones. So if you look at thorium, we know that thorium is element 90. And we're saying that it's 231, so it has 231 particles in its nuclei. So that's the first step. So that would be getting that correct. And then you would decay it. So decaying it means it's going to transmutate or change into another type. It's going to give out an alpha particle, as I say. So you can put an alpha particle. Now you could put either that symbol or helium. Doesn't matter to me, both are correct. Okay, and then you'd have to find out what the missing element is here. So you would go, okay, 231 minus 4. So 227. And then you go 90 minus 2, 88. So to get the proper symbol, you would look up element 88. All right, so looking at the periodic table here, element 88 is radium right in the corner of the bottom here. Right there by my top finger. Okay, radium. So that's how you do that one. Okay, now radium's element, oops, we already did the plus sign. Throwing in too many plus signs. Just put element radium. Let's do another one with, I'll do the other particle so you see both of them. So let's say, write the beta decay we'll use the same thing for thorium. 231. Okay, so we start the same way. Okay, we throw in the decay. So now we write our beta decay. So this is an electron taking a proton and making it an electron, basically, is beta decay. So put our beta decay in here. Okay. Now the only thing is the top doesn't change. But in order to get 90 on here, we have to have one more so that we have 91 minus 1 gives us 90. So this is going to be 91 down here. It's going to go up 1 in protons. So let's take a look. 91 here on our periodic table. Down here, it's proctorium. Ooh. Proctinactum. Proctinactum. Or PA. Probably none of us have ever seen it, including me. Okay, it's right before uranium. All right, so that is the first one from the modern physics selection. Okay. Okay, the next type of question, 2 more to go here. So I'm going to do a binding energy and a nuclear equation energy in there. So we'll do an example of how that happens. So calculating of energy release, okay, using when nucleus splits. Or when a nucleus binds? Oh, sure. Going a little too fast. Okay, so just to mention it, I'll talk a little bit here. This is the big area of the modern physics, the using the E equals mc squared, so totaling up one side of the equation and the other side of the equation, or doing a nuclear binding energy. In fact, they probably will have both on there. Okay, now I did send back a bunch of the Fields unit hand-ins that you guys did as well, so those are put into the thing. So I think everybody's in good shape going into the final. And the final's not a huge amount, but if you want to maintain your 90 or 80 or 70 or whatever you're shooting for, you know, it's a good idea to prep up for your final exam. Okay, so let's do a binding energy one, which is basically the same as a nuclear fission or fusion. They're both the same, so basically you're totaling up one side of the equation. The harder one would be binding energy, so let's do a harder one. Let's do an atom of binding. So now you don't have to memorize these or write them on your formula sheet, but protons equal 1.6726 times 10 to the negative 27 kilograms. Neutrons equal, now I have this in 4.9 in the question. Now the key is all the masses will be given in the given question, so you don't have to look them up. So as soon as you see some masses in there, you can clue in, okay, I'm going to be using E equals mc squared, and I'm going to be calculating a mass difference from one side to the other, or from the nucleus mass to the sum of the particles mass. So you're going to do that. So let's do an example. Let's do a helium particle. I think I've got a helium particle somewhere. No, let's just look one up. Let's just say, what's the mass? Let's do K19. That's potassium 19. So potassium 19 is a nuclear particle, so its mass is, let's see here. All right, so it's oh, it doesn't stay here. Oh, there. Right. 1.66, or sorry, the mass equals 6.4924 times 10 to the 26. Right there. Okay, so let's stick that in. So let's say K19 has a mass for its nucleus, because it's not the whole atom, of, okay, according to the internet, we got 6.4924 times 10 to the negative 26 kilograms. And there we are. Okay, we can close that part down now so I can see chat. Okay, so there we have that, and then I'm going to ask the question, what is its nuclear binding energy? Let's move my brains over here. Okay, so what is its nuclear binding energy? Oh, spell this right. Okay, so I might ask, what is this? Well, I will ask of nuclear binding energy. Okay, so we have to know how many protons it has. So this K19, so K19, and we have to look up what is K on the periodic table. So if we look on our periodic table here, let's bring myself back over here. Okay, so on this periodic table, K is element number 19. Okay, wait, I can't have K19 there, but I better change that. It is element 9. Oops. There we go. So let's put 19 there. Let's change this to a larger one. And I'll look up a larger one because we want some neutrons in there. We just don't want protons. We could do K19 on its own, but typically, I don't know why I thought K19 was a good idea. Let's do K30, I think 38. Let's do 39. We'll do one more. Nuclear binding energy. Nuclear mass. Sorry about that. I was thinking K19 being element 19. Okay, so we'll change that mass there. Okay, so according to this one, there's a better one. Okay, so we'll, there at 6.4682. So we got to change this a little bit. Okay, so let's change this to a 39. Sorry about that, guys. I don't know why I was thinking just with 19. Oh boy. Probably because it's Friday. All right, so this is 39, and this is a little bit heavier. 4, 6. It has a lot more nuclear binding energy. 4, 6, 8, 2. All right, so there we go. Let's go back to the calculation. So this is not a 19, this is a 39 up here. So we'll switch it. Okay, so that gives us our, we've got 20 protons, or sorry, 20 neutrons. And 19 protons. Okay, so that's what we're going to total up first. So we're going to total the mass. Okay, so we'll take our neutrons first. And we'll multiply it by 20. Okay, so we'll take our calculator, we'll multiply that by 20. 1.6749 to the scientific notation of negative 27 times 20. Whoops. at 9 times 20. Okay, so I get 3.3498. Okay, and it's times 10 to the 26 kilograms. Okay, and then underneath it, we'll do the protons. So they're a little bit lighter. Okay, now the protons, there's only 19. So those two things will total up to 39. Okay, so we go 1.67, 26, scientific notation button, negative 27 times 19. Okay, and we get 3.1779. 94, but I'm not going to put the 4 in there. We're just going to use the same amount, the 5 significant figures. And this is all kilograms. Okay, and then we're going to total these. Okay, so 3.3498 times 10 to the negative 26 plus 3.1779 times 10 to the negative 26. And this gives us a heavier mass, 6.52777. Okay, so notice this is heavier. Okay, so that means there's some missing mass or a mass defect or deficit, depending on how you say it. And then we can take the difference. Okay, so now we're going to take the difference between our one that we looked up, K39. I don't know why I started with K19, but that's just how it goes. We're going to subtract the difference. So we're going to take the total, and we're going to subtract 6.4682 times 10 to the negative 26. Okay, I'm not going to use the extra 1 there. I'm just going to use 5 significant figures. And this is the nuclei. And these are the heavier parts. Okay, so now we're going to take that difference. So we take 6.5277 scientific note 6.5277 scientific notation button negative 26 minus 6.4682 scientific notation button negative 26, and we're left with 5.595 times 10 to the negative 28 kilograms. Okay, so that's the missing mass that we're going to convert into energy, nuclear binding energy. Okay, so then we convert it using Einstein's equation. Let's slide this up a little bit. So Einstein's equation, this is our missing mass or our mass defect. Okay, so that's this energy. Okay, remember that c squared is equal to 9.0 times 10 to the 16 meter squared second squared. Okay, And you're going to end up with joules because meter squared, second squared times kilograms is a joule of energy. Okay, so then we've got this mass times c squared, which always turns out to be 9.0 times 10 to the 16 meters per second squared each, because we just square the constant of light. So we go times 9 exponent 16, and we get 5.355 times 10 to the negative 11 joules. So that's what's holding that nucleus together. Hey, sorry about starting a little slow there, but that's that second. So there's only one left now, type of question that's going to come into the, again, using the modern physics, the last 4 days that we did. It's going to be a half-life. Okay? So maybe you'll want to include the half-life. There's no really set formula for it, but depending on how it's written, I would write this equation because it makes it a little bit easier to use an equation rather than trying to do logs or something like that. So the final thing that that's going to show up is half-life. So just remember what half-life is. So if we're doing the original activity equaling the activity times the half-life to the power of n, I think I used decimal 5, where this is time over half-life. So you might want to include that, and this is your, I think I got these ones are backwards. Let me just make sure I'm not telling you a fib here, and I'll just look it up real quick, making sure I don't have those two backwards. So we'll just take a look here. Yeah. According to our equation here, if we look back in here, oops, and go into our modern physics here. Okay, just to remind ourselves so we don't get it backwards. I don't want to get it mixed up. Oh, no, that's the next day, I guess. Can't read my own writing. Half-life, there we go. Okay, so NO is on the inside. So the original one's on the inside. So let's make sure we get it right here. So this is our NO on the inside. Okay, don't have to memorize that, so write that into your, all right, write that into your equation. So there'll be a half-life, one half-life one. So our final thing for today and for this final exam is looking at half-life. So let's do a half-life one. Now the one on the exam that I'm going to use is going to be carbon-14, because that's what we traditionally use. So I'll use a carbon-14 atom here in our example as well, just for studying. So we'll do a similar one to what we would have there. Okay, I'm going to slide this up a little bit to the top. Let me know if I'm going a little fast. Okay, so we're going to do a half-life one. Okay, so I'll model it like the one that is on the exam. I'm going to type this one. I don't know why, but So let's say C14 has a half-life of 5,700 years. I think it's actually like 5738, but we're going to round it off. Okay, so if a sample originally oops, there we go, forgot an I, has an activity or mass. I could do activity or mass. Both are the same. Has an activity of, let's say, 305 becquerels. And later, its activity is, let's say, 40 becquerels. How old is the sample? So this is, if you're thinking about this is a fairly accurate way of dating, but some critics of it still say, well, how do you know what the original sample was, right? You weren't around X number of years ago to take samples. So, but what they do is they do estimates of activity means how fast it's decaying. So when you have, if we look back at in physics, activity or mass, so you might have a mass of nuclear or radioactive material, okay? And what activity means is the radioactivity. It's a short form of radioactivity, okay? So they'll often use activity. So what's happening in radioactivity is it's giving off so many particles per second. So a becquerel is 1 decay per second. So in our example, it starts out at 305 decays every second. So it's fast decaying, losing mass fast. And then later on, it slows down as the mass will go down. So you can have a mass or an activity in this question. That's why it's NO and N rather than M and M, because it could be activity or mass. So the N just stands for nuclear decay. Original nuclear decay and future nuclear decay. Does that make sense? So that's what that is. This is decay per second. Okay, so if we're doing that, in our case, we know that the half-life, let's make it skinnier here. Okay, our half-life is 5,700 years. Our nuclear original decay rate is 305, named after the guy Becquerel. And after some time in the future, it's only 40. Okay? And basically, we have to calculate. We have to find out what N is. Okay, so it's an easy setup for us. Future rate. Original rate times the half-life or you could use 0.5 because that's what most people will use because they're going to use their calculator, right? So we've got to divide this out. Okay. Okay, so we go 40 divided by 0.305. So we get 0.131. We'll go 4. 131 is good enough, I think. We'll go 3, because I only have 2 significant figures there, and 3 there. Okay, and then this is, we'll go 0.5 to the power of n. So now what you do is you can guess and check. Or you can use logs. If you took Pre-Cal 30, you can do logs. Okay, so I'm going to do guess and check because most people, not everybody took Pre-Cal. And then I'll do logs as well, just to show you. So we're going to go, well, let's try n equals 3. Okay, so 0.5 to the power of 3 is equal to 0.125. So that's a little bit smaller than this, right? Okay, so it's not going to quite be 3, but if you went with 3, it'd probably be close enough. So you could try, or sorry, this is a little bit bigger. So let's try 3.1. Okay, so n 0.5 to the power of 3.1. Oops, I went the wrong way. I've got to go down. What was I thinking? That's up high. Let's try 2.9. 2.9. We're guessing and checking. So 0.5 to the power of 2.9. Hey, there we go. That's 0.133. So is it closer to 0.9 or 2.9 or 3? It's closer to 2.9. So we say that n equals 2.9. Now that's how many half-lives you have. Okay? So now you would have to figure out the time. So now you know that n equals time over half-life. So if you rearrange that, because you know n, you know that the time is just equal to n times the half-life. So you're going to take your answer and multiply it by your half-life. So my answer, 2.9 times 5,700. Okay. So 16,530. Okay, now if you did logs, I'll do it in blue. Okay, so if you did log, let me skinny that up first. If you did logs, if you were in Pre-Cal, you could have went log 0.131 equals log 0.5 to the power of n. So this, you could bring the n out front. So we're just going to divide the two. Okay, so you go log 0.131 divided by log 0.5, and I get 2.93, which is the same as we guessed. whichever way you like doing it. It doesn't matter to me. And that's it. That will be our final exam. So now the final exam is sent. This morning I sent it out to your supervising teachers. You have a 3-hour time limit. It should take you around 45 minutes to 2 hours, depending how prepared you are. And it's not an overly ambitious exam. It doesn't have every single thing on it. We did the outline so you can focus your study, okay? So that's to your advantage. You kind of know what's coming. So the rule that I have with formula sheets is make sure that you make your own there. Remember, I will have a periodic table for you. You don't have to worry about that. Okay, I sent this with the exam for the nuclear physics part at the end here that we did. Okay, and but you have to make your own formula sheet. So I'm not a big proponent of somebody photocopying somebody else's because the whole point of me saying you can do a formula sheet is it's a way for me as an educator to get you to do some preparation work. So you're preparing. So by doing that, you're actually reviewing and thinking and getting ready and all that and feeling stress and getting all that stuff ready. So if you don't do any of that, you shouldn't have the advantage of having one of those in front of you. So my rule is you've got to do your own, and also you can put anything on there except for examples. So you can't just copy my review down onto the sheet kind of thing. You have to kind of do the formulas and little notes and maybe steps that you follow. Okay, before I let you go, I will check in with everybody on Monday morning to see it. We won't have any more class, but I will check in to see how things are going. So you can I'll dial in for a bit and ask if there's any questions on Monday. And then we'll see from there if there is any questions. Okay, so now it's just preparing. Now, in terms of writing your exam, it can happen any day now. Most schools will have it in their exam week so that students have time to study. This following week coming up, you can study and prepare. In Vanguard, our physics exam is on we've got ours scheduled on the 27th. Okay, so that's when, for anybody that, I know that I said I don't have any Vanguard people here, but it's got physics scheduled on the 27th, just because we use the old, I don't actually have anybody writing it, but we scheduled it in. But if you write it a different day, I don't care. As long as I get it by the 29th or on the 29th. So even if you give it to me, I have to have my report cards done for you guys on the 29th. But even if I get it on the 29th, there's only 12 students in physics or something like that. So I could get everybody marked and finished as long as I got them. Okay. Any questions then before I let you go? That's basically it for today. All right, I'll let you go and I'll check in on Monday to see if anybody's got questions. But our review is done now. See you. Have a good weekend, everybody.